All right, let's get started. Yeah, so the title of my talk today is Ramanujan and Mach theta functions pre-2000. I'm going to try to get us all the way up to Zwegers' thesis and then not talk about that today because that will be the subject of a future talk. But I wanted to just spend maybe 5 minutes on something that I didn't quite get to last time. Just one interesting example that I think is kind of fun. It doesn't really fit in the rest of my talk today, so I'll just do it right at the beginning. So if you recall, at the very end last time, I talked about Zagier's weight 3/2 Eisenstein series. And the holomorphic part encodes the Hurwitz class numbers. These are just regular class numbers, but there's some kind of weighted sum. You would divide by 1, 2, or 3, depending on the number of automorphisms of some quadratic form. Maybe don't worry about this so much. The point is that these H numbers are class numbers. And so this weight 3/2 non-holomorphic Eisenstein series encodes somehow the class numbers, the class numbers of imaginary quadratic fields. And we saw that through the class number formula, because in the formula that came up, there was some kind of special value of some kind of Dirichlet L function. So, right, so this was like regulator times class number. And that's how that arose here. Okay, so I want to think about this in a slightly different context. So there are really two weights here. There's weight 1/2 and weight 3/2. And in weight 1/2, we have theta, and then we have this H, and these are connected by the C operator. Okay, well, it's not exactly theta, it's maybe -1/16 pi theta, but I'm going to ignore the constants. Since theta is a holomorphic modular form, it's annihilated by C1/2. Okay? And now I've drawn this diagram, hopefully somewhat suggestively, because maybe there's a little bit of room up here for something else. And that would be some kind of preimage of C1/2 in weight 1/2, if such a thing exists. And it turns out that such a thing does exist, and this is a theorem of Duke, Imamoglu, and Toth. So I'll just briefly write up a statement of the theorem, and there's a much more detailed version of this theorem, but I'm just going to kind of give you the big idea. So maybe let's call this thing, I'll call this thing H hat. So theorem of Duke, Imamoglu, and Toth. There is a function H hat of weight 1/2 with C1/2 of H hat is equal to H. And even more importantly, the holomorphic coefficients, or maybe I'll just say the holomorphic part of H hat encodes real quadratic class numbers. Weighted by the regulators. Sort of running out of room at the bottom here. So, okay, does it really encode the real quadratic class numbers? No, because you always have this sort of thing where the class numbers and the regulators always come together. So what it really does is it encodes real quadratic or special values of real quadratic Dirichlet L functions. But this is a really beautiful theorem. So, okay, this is not a harmonic Maass form. This would be an example of what Michael was talking about, a sesquiharmonic Maass form. We're probably not going to talk about these too much more, but there are some interesting examples. And to be honest, this is a theory that that essentially just doesn't exist. I mean, there are a couple of papers here and there on sesquiharmonic or higher depth harmonic Maass forms, but there's really, I think, a lot of interesting questions and maybe a lot that we don't know. And I would love to know more about these sorts of things. But this is, I think, a pretty picture that just goes nicely with what I talked about last time. Are there any questions about that? All right. So now I'll switch gears and let's start talking about Ramanujan and Mach theta functions. Now, I'm not going to spend too much time on the historical story because Professor Murty did such a good job of this, explaining the story between Ramanujan and Hardy and the two letters. So I'm going to focus today on, I'm going to try to focus on 5 examples that came up because of Ramanujan's last letter to Hardy, and maybe one question that arose because of each of these examples. And then hopefully in my next lecture, I'll try to answer all 5 of those questions in the sort of modern language of harmonic Maass forms. So today I don't actually have a lot of answers, I just have a lot of questions, mysteries maybe that came up because of the last letter. So any discussion of Ramanujan has to start with partitions, I think. So let's do that. So if we look at the generating series for partitions, this is the infinite product that has shown up several times before, 1 minus q to the n to the minus 1. This is the essentially the inverse of the Dedekind eta function, so that will come up in a minute. And then another formula that has come up a few times is this equivalent generating series. Let's see, we have a q to the n squared, and then let's see, 2 copies down here. Let's see, 1 minus q squared, 1 minus q squared squared, 1 minus q to the n squared. And this second formulation comes from thinking of a partition in terms of its Farrer's diagram, in which you have a Durfee square of size n squared, and then off to the side, there's another partition that is restricted by having fewer than n parts, and then another partition down here that is also restricted by having fewer than n parts, though it's sort of turned that direction. And so by breaking a partition into these 3 pieces, these 3 pieces correspond to, well, there's the n squared from the Durfee square, and then we have 2 partitions into parts of size, or into fewer than n parts. This formula is going to appear again, or something very similar to it is going to appear again very soon. So that's why I wanted to bring it up. Okay, so Hardy and Ramanujan. Hardy and Ramanujan were interested in the question of how big is P of n as n gets close to infinity. And so they developed what we now know of as the circle method. And let me just describe very briefly the circle method. If you've never seen it before, let's maybe even do a little example, like a little toy example. So the idea behind the circle method is if we have some Q series, say with coefficients a sub n q to the n, then by Cauchy's integral formula, I can pick out a sub n by a contour integral. So I can integrate over some circle of radius, let's say radius r. I just need r to be less than the radius of convergence of G, whatever it is. And then I'll integrate G of Q over Q to the n plus 1 dq. And that's going to pick out the nth coefficient. And of course, if we apply this to the generating series for P of n, well, that will give us a formula for P of n. Of course, that requires you to actually know something about the generating series, so we'll get to that in a second. But this is the idea behind the circle method. So maybe let's actually just run through the details of a toy example really quick. So partitions are complicated, so let's do something quite a bit simpler. So let's let P3 of n be the number of partitions of n into parts less than or equal to 3. Okay, so the only numbers you're allowed to use are 1, 2, and 3, and we're just going to compute the number of partitions of n into parts less than or equal to 3. So the generating series for this is just, well, it's going to be this product, except it's not the infinite product. We're just going to take the first 3 terms of this product. So it'll be 1 over 1 minus q, 1 minus q squared, 1 minus q cubed. Okay? Well, this is a nice clean formula, and it's going to let us do something in this case that you actually can't do in the case of partitions, but I'll explain that in a minute. So P3 of n is 1 over 2 pi I, integral over absolute value q equals r, g3 of q over q to the n plus 1. I'm just using this formula here, and let's say we start with r less than 1. So we're going to integrate, and specifically we're integrating in the counterclockwise direction. Okay, so that will pick up the nth coefficient, and now what we're going to do is move the contour. We're actually going to move it out past the unit circle. But of course, this function has poles. Poles at, well, there's a pole at q equals 1, certainly. This is a third order pole. It has a pole at q equals minus 1. That says 1 again. Q equals minus 1, that's order 1. And then it's got poles at q equals, let's say, zeta 3 and zeta 3 inverse. These are both of order 1, and zeta 3 I'm just saying is the primitive third root of unity. Okay, so these are the poles, and now what we'll do is we'll take the contour and just expand past those poles. And we're allowed to do that because this function still makes sense even for q bigger, or for absolute value q bigger than 1. So we can actually expand past those poles. Now, this is something you can't do in the case of the partition function. And so the circle method is quite a bit more complicated in that case. But here it's quite nice, and you can kind of see exactly what's going to happen. And so what we'll do is we'll take r bigger than 1 now. And when we do that, we're going to go past these poles. And so the residue theorem says we're going to pick up the residues. And you got to be careful because, let's see, we were integrating counterclockwise. And when we pick up those poles, we're actually going to kind of pick them up in the wrong direction. So we're going to get minus the sum of the residues plus another integral. And I won't write all of that again because it's the same integral, it's just r is now bigger. But actually, well, what was stopping us from just going slightly outside that circle? Why don't we just keep going? Why don't we just take the limit as r goes to infinity? So if we take the limit as r goes to infinity, well, it's not too hard to see that the integrand is going to go to 0 quite rapidly. And so this integral actually just vanishes. And so we just get that this equals the negative the sum of the residues. Okay? Well, let's actually compute the residues. Let's do it. Why not? So minus the residue at q equals 1 of g3 of q over q to the n plus 1. Well, let's see, this is going to be 1/2 limit as q goes to 1 of the second derivative with respect to q of, well, we have to cancel the 3 bad the three bad 1 minus q's. So we're going to cancel all of those. And what we're left with is, let's see, 1 plus q. And then when we cancel the 1 from the 1 minus q cubed, it's going to be 1 plus q squared. And then I still have this q to the n plus 1. Okay? And now if I actually do those two derivatives in front of you, I'm going to definitely embarrass myself. Nobody wants to see that, so I'll just tell you the answer. This is maybe a fun calculus problem to do. So 1/12 n plus 3 squared minus 7 over 72 is what you get. You know, I don't know why the 7 over 72 has to be there, but it just is. Happens. Okay, and then we can do the same thing for the other two, and maybe I won't bore you with the details, but the point is that if we put all of these together, what we end up with is an exact formula. So there's the one that we just computed. You also get a minus 1 to the n over 8. That comes from the pole at q equals minus 1. And then you get a 2/9 cosine of 2 pi over 3. And that comes from computing the residues at both of these and summing them together. You end up getting the real part of some root of unity. That's where the cosine comes from. It's not even clear that this is an integer, but it has to be. It looks like potentially just a rational number, but it's an integer for every n. And there's an exact formula. And in fact, not only is it an exact formula, but if you ignore all of this at the end here, what it's really saying is that for large enough n, p3 of n is the nearest integer to this number here, which is quite nice. Yeah, there is. It's n, 2 pi n over 3. Thank you. Yeah. Yeah, that would be silly if there wasn't an n on there. What's that? Read it out. Yeah, so it's minus 1 to the n over 8, and then 2/9 cosine of 2 pi n over 3. Okay, so that gives you an idea of the power of this thing that Hardy and Ramanujan invented, the circle method. Now, what happens for P of n is that, okay, for P of n, there's a natural barrier at q equals 1. And there are singularities of this function. This function has singularities at every root of unity. And we're not allowed to expand the contour any farther than the unit circle. So what you have to do is just get very close and then approximate. And if you can do that well, then you can get information about P of n. Now, what happens here is that, okay, I just told you that there are poles at every root of unity, but they're sort of weighted by the denominator of the root of unity, or the denominator of the rational number that corresponds to the root of unity. This pole at 1 is really big, or at least it has a lot of weight. And the pole at minus 1 is maybe half the size. And then there are poles at I and minus I, and they're a bit smaller. And then there are poles, right, at the third roots of unity that are, right? And you need to sort of measure, when you do this, you have to sort of measure how big, like how close you are to rational numbers that have small denominator to see how big the pole contribution is. You have to do this very carefully, and it takes a lot of effort. There's a scene in the film, I don't know if you've seen the film, The Man Who Knew Infinity, but there's a great scene where Ramanujan comes in to Major McMahon's office, and he's computed P of 200 using the circle method. And Major McMahon also has computed P of 200 using a table. And Ramanujan reads it off to him, and McMahon just says, "Oh, you're within 2%. And if you actually use the circle method, you'll get way better than 2%. But I think for the purposes of an audience that's not mathematicians, they didn't want to say, you're within 10 to the minus 9%, you know, like, I don't know. It's very, very, very close, right? So it's even better than the 2% that it says in the film. But anyway, that's a scene of them doing just exactly this thing, which I really like. All right. Yeah, so I should tell you what you might get. Okay, so yeah, how do we actually access these points here? The Q expansion, so remember Q is e to the 2 pi I tau. So in the Q disk, tau tau equals equals I infinity is right here at q equals 0. This is where the q expansion is centered. So all of our information is here. How do we actually access the things over here? Well, we access them using the fact that we know the modular transformation behavior of the Dedekind eta function. So in particular, eta of minus 1 over tau is square root of minus I tau, eta of tau. Have I ever actually written down the definition of the eta function? Maybe it makes sense to do that at some point. So this is q to the 1/24th times that product that I already had written. So using this, it can take you from this 0 point, it can take you to 1. And that will give you, if you just do this transformation, that will give you the biggest contribution from the circle method. And what you end up getting is that P of n is asymptotic to, I definitely don't have this memorized, 1 over 4n root 3 e to the pi root 2n over 3. And that's if you just consider this really big pole. And then you can keep going and you can get more and more lower order terms. And that's what Hardy and Ramanujan did. And they wrote down an infinite series such that if you truncate that infinite series at, say, square root of n terms, you'll get something that approximates P of n very closely. The problem with this infinite series is that it's divergent. You can't actually take all of the terms together. And so several years later, Rademacher came along and he fixed this. And he was able to get an exact formula for P of n. So P of n equals 2 pi over 24n minus 1 to the 3/4. Sum c bigger than 0, a c of n over c I 3/2 I squared of 24n minus 1 over 6c. And this is an exact formula now, an exact infinite series. And to do this, Rademacher, well, he had to be pretty clever with the circle method. And he had to really think, well, okay, the circle method still works if the contour actually isn't a circle. All that really matters is that you integrate around 0. So he decided to integrate in a very clever way. And the thing you want to look up if you're interested in this story is you want to look up Ford circles. These really live in the upper half plane, but they're sort of circles centered around rational numbers with differing radii depending on the denominator of the rational number. So, and using the Ford circles, he was able to actually make this work all the way. Now, I need to tell you what all the pieces of this formula are. We've actually seen everything before in previous lectures. They just maybe didn't look like this. So AC of n is a Kloosterman sum. And this is actually one of the Kloosterman sums that we've seen already. I just didn't call it AC of n, I called it something else. I called it something SMNC nu. And for AC of n, you plug m equals 1 and n equals really 1 minus n. And then I think maybe you're off by some root of unity here, so I'll just ignore that. But we've seen this already, and here this is the Dedekind eta multiplier system. So this is exactly the Kloosterman sum that shows up in the Fourier coefficients of the Poincare series that I wrote down yesterday. Okay, and in fact, you can give a proof of this formula using Poincare series entirely. You don't actually need the circle method to do this. Then that's maybe kind of like a modern approach that uses Poincare series. It would be a Poincare series of weight minus 1/2 with the eta multiplier. Let's see, what else? I 3/2, well, this is the I Bessel function. As c goes to infinity, this looks approximately like c to the minus 3/2. Okay? And AC of n, let me tell you, let me actually write down the formula because I want to look at it. So it's the sum over all the d's mod c that are co-prime. That looks familiar. And then there's this piece here, e to the pi I s d c. This is what's called a Dedekind sum. And this is essentially the Dedekind eta multiplier system. It's not entirely, but that's essentially what's happening there. And then e of minus dn over c. So this looks very familiar. And notice that there are at most c terms here. So the worst case scenario is that AC of n is of size c. Well, that cancels that c. So if we're thinking about how big this is, those are sort of gone. And now we have a c to the minus 3/2, so this converges quite nicely, absolutely. Okay? So convergence here is not an issue, but it is known. Yeah, that's actually the next thing I'm going to write down. So yes, perfect question. So that is known. But yeah, I just wanted to point out that it's not necessary to prove convergence of this, right? Yeah, but I want to write down a formula here, and this is a formula of Whiteman. And I'll also put Selberg's name on here because in Whiteman's paper he said, Selberg figured this out, but he didn't prove it, so I'll prove it. So anyway, apparently he attributes it to Selberg. Oh, really? Oh, interesting. Yeah, okay. Anyway, the formula looks like, well, square root of c over 3, and then a sum over b's mod, I can never remember this, 6c, such that b squared is congruent to 1 minus 24n mod 24c. Okay, this is a sum this also showed up. Something that looked like this showed up yesterday. And I called it Conan's formula, Conan's identity. And it was relating a Kloosterman sum associated to the plus space to some kind of sum with a square. It was a b squared is congruent to some discriminant, okay? This is essentially that formula. It's just for a different multiplier system. These are just two glimpses of sort of the same exact thing. So what goes in here? Well, just a character, 12 on b, and then an exponential term. Nope, it's a cosine of pi b over 6c. Okay, so actually at this point we can prove that the Kloosterman sums are no bigger than square root of c approximately, because this sum is sparse. There's not very many b's that satisfy this quadratic congruence. And so you can show that this bit here, this is no bigger than like c to the epsilon. This is very small, and of course there's a square root of c here. And so this whole thing is just visibly less than c to the 1/2 plus epsilon. So you can do quite a bit better than the trivial bound. But again, we don't actually need this to prove the convergence of the Rademacher formula. Okay. Yes, there is a paper that's essentially all that paper does. I'm trying to think of Probitkin, maybe. Does that sound right? You can ask me after, and I can definitely look it up for you if you'd like. Okay, so I haven't talked about Mach theta functions at all, so maybe we should get to that. So now let's go to 1920. Ramanujan is on his deathbed. He writes a letter, Hardy from India. And whereas Ramanujan's first letter to Hardy was quite long, many pages, and had many, many formulas in it, Ramanujan's last letter is quite short. I think it's maybe 4 pages. And it has a little bit of him talking about these mysterious things, which he calls Mach theta functions, and maybe sort of a definition, and then just 17 examples, and a couple of formulas. And it's really an enigma. So let me tell you about one of the first functions that shows up. It's called f of q. And this is going to look familiar, not just because it has shown up in previous talks, but because it's essentially right there. So I'm just going to write that generating series for P of n, but I'm just going to put plus signs instead of the minus signs. Okay, and this is called f of q. And for later use, I'll name the coefficients of this thing. I'll call them alpha f and q to the n. Okay, so Ramanujan says that f of q is an order 3 Mach theta function. And he, in his 17 examples, he puts them in 3 boxes, order 3, order 5, and order 7. And don't ask me what those mean because I don't know. I just think that they're a good labeling system, but I don't really know what the order is. Okay, so what can we say about f of q? Certainly, it looks tantalizingly close to something that's very nice, that's a modular form. So you might think, your first thought might be, well, this has to be something like a modular form. It's so close. Okay, so, well, first, maybe a first question is, does this relate at all to partitions? And the answer is yes, it does. So alpha f of n counts the number of partitions of n with, is it even minus odd or odd minus even? It's even minus odd. With even rank minus the number of partitions, I'm not going to write all that again, with odd rank. And what's the rank? So the rank of a partition, say lambda, is the largest part of lambda minus the number of parts in lambda. Why is the rank a thing that we care about? Well, it gives a combinatorial explanation for one of Ramanujan's famous theorems. So it explains Ramanujan's congruences, at least mod 5 and 7. So the congruences are P of 5n plus 4 is congruent to 0 mod 5. And P of 7n plus 5 is congruent to 0 mod 7. There's a third one for 11 that is not explained by the rank. And there's a great story there that I will not be getting into today. But there's a cool story there. So the rank is something that, like I said, explains the congruences. And if you count the number of partitions of n such that the rank is even, and then subtract the ones that are such that the rank is odd, you get the coefficients of f of q. So certainly there is something interesting going on here. Ramanujan writes down without proof, in Ramanujan style, writes down without proof that alpha is asymptotic to -1 to the n minus 1 over 2 squared of n minus 1 over 24, e to the pi square root of n over 6 minus 1 over 144. Okay, so he gives an asymptotic, at least a highest order asymptotic formula for alpha with no explanation, and presumably maybe he used some kind of circle method here as well. I don't know if we know that. But remember, what did we need for the circle method? We needed the transformation law for the Dedekind function. So maybe that's something that we need here for f of q, and that's going to come up in a minute. But we also needed information about the Dedekind function at its singularities, at the exponential singularities. And this sort of leads into Ramanujan's definition. I'll call this Ramanujan's definition of what a Mach theta function is. This isn't exactly how Ramanujan wrote it, but I think it captures more or less the spirit of what he said. So a Mach theta function is it's a function, f in the upper half plane to the complex numbers. Here I'm thinking of this as our tau variable, And then our function will probably be a Q series, and so Q should be, as usual, e to the 2 pi I tau. And for Ramanujan, I think he wanted these functions to be in Eulerian form, whatever that means, so some kind of form that kind of looks like this. And Atul talked about Eulerian form yesterday. And I'm not going to include that in the definition, but I think he wanted that in the definition. But it needs to satisfy 3 properties. The first one is that F has exponential singularities at infinitely many roots of unity. And of course, when I say roots of unity, I'm not talking about the tau variable. I'm saying in Q roots of unity. What's that? Thank you. Yeah. The second one is that for each root of unity, and we'll call our root of unity zeta. Oh, that's not a zeta. There we go. Root of unity zeta. There exists, and I'll put this in quotes, a theta function. And that's what Ramanujan called these. But really, I think for Ramanujan, a theta function is just sort of a weakly holomorphic modular form in today's terminology. So there exists a theta function. We'll call it theta sub zeta. It's allowed to depend on this root of unity, such that f of tau minus theta of tau. Well, this thing, theta should cut out the exponential singularity. So this should be bounded as Q goes to zeta. We're thinking of Q going to zeta radially from inside the unit disk. Okay? And then number 3, there is not a single theta that satisfies 2 for all zetas. So you can't use the same theta function for every single root of unity. Okay? And this leads to my first question. I said that I was going to have 5 questions today, so here's my first question, which is, what are we supposed to do with this? Like, what are we supposed to make of this definition? I don't see a lot of structure here in the same way that the definition of a modular form clearly has some structure. There's like a clear vector space structure. There's clearly an action by a group, right? There doesn't seem to be any sort of group theory in here. So what do we make of this? And what I'd really like is to see some structure. So that's question number 1, which is, what do we make of this definition? He did? Oh, who proved it? Yes, this was proved by Watson, maybe? Is that right? Oh, yes. This is Dyson's gadget. Actually, was it Dragonette? So I know that. So I'm going to say Dragonette's name in a minute for a larger asymptotic formula for f of q. She might have actually been the first to prove this in the first place. I'm not sure. That's a really good question, and I don't know off the top of my head. I do know that there is a paper of Brinkman and Ono that deals with the rank generating function and asymptotics, and but by pure thought and just by thinking combinatorially and this subtracting the even minus the odds, I don't know. That's a great question though. Okay. Are there any questions at this point? This is a good place to pause. Yeah. Oh, it's like you're just putting words in my mouth. You're just saying the next thing. Yes, there is. And we're going to get to it in like one more page of notes. Yes, an analog of the Rademacher formula for f of q. Yeah, we're gonna see that in just a sec. Oh, for a given Mach theta function, how many theta functions would you need? Let's see. For f of q, I believe it's 2. Is that right? You just need 2 theta functions. So it's like as close as you can get to being not satisfying this because you just need 2 of them. I don't know for all 17 examples how many you need for each one off the top of my head, but for f of q, you just need 2. I don't know. That's another good question. Yeah, I don't know if there's an example where you need infinitely many. I would imagine that the answer is no, because if it's modular for a congruent subgroup, something that's finite index, then you should be able to look at these roots of unity in classes, and you should be able to use 1 theta function for each of the finitely many classes. That's my general sense. Yeah, but that's not something I've thought of before. Okay, so let's talk about the other Mach theta functions. So there are 17 Mach theta functions, at least in the last letter. And they are in 3 orders. So there's order 3. And there are 4 examples, including f of q and some others. There are some that are called order 5. And there are 10 examples there. And then there are some order 7s. And there are 3 examples. Maybe I'll write down for you one example of a 5th order one, just so we can look at it. So this one is called F0 of Q. By the way, Ramanujan's letter is sort of notorious for reusing the same letters over and over again. So this one in Ramanujan's letter is called F of Q. So the subscripts were added later so that there's no confusion. So this one is F0. It is the following sum from 0 to infinity of Q to the n squared over, and I'm going to use the Pockhammer notation now, QQ sub n. And here's what the Pockhammer notation is for reference. AQ sub n is a product m equals 0 to n minus 1, 1 minus AQ to the n. Okay, so that's one of the 5th order functions, and we'll see that one again in a little bit. There were other Mach theta functions that Ramanujan wrote down in what's called his lost notebook. It's not actually a notebook. So it's just a collection of sort of loose pieces of paper that George Andrews found in Watson's office after Watson died. So in 1976, George Andrews went into Watson's office, and there was just stacks and stacks of math papers, and he just carefully looked through things and found a box full of Ramanujan's writings, just loose pieces of paper. And so we call this the lost notebook because it isn't really a notebook, but it's sort of like one of Ramanujan's notebooks. And it has lots of other examples of Mach theta functions. And there have been others that have been discovered since then as well. So for today, I'm just going to talk, and for tomorrow, I'm just going to talk about these 17, but you should know that there are others. Though actually, maybe I will mention one other one that was discovered in the Lost Notebook. So the Lost Notebook, there's another order 3, and it's called omega. And we saw omega in Atul's talk yesterday. So let me write it down. Q to the 2n times n plus 1 over q squared sub n plus 1, and that's squared. And the reason that I bring up omega is that there actually does appear a transformation law for F in the Lost Notebook. And it looks like this. And I'm going to write it in sort of the classical way. This isn't really the modular forms way, but this is how I'm going to write it. So if Q is e to the minus alpha and Q1 is e to the minus beta, where alpha and beta, when you multiply them together, you get pi squared. So alpha and beta have sort of an inverse relationship. Let's say alpha is a complex number with real part bigger than 0. Then Q to the minus 1/24th, f of Q, is equal to 2 square root of 2 pi over alpha, Q1 to the 4/3 omega of Q1 to squared. I know it's really fun to watch people just write complicated formulas on the board, but this is just kind of complicated. I'm just going to do it. So if I stopped here, it would look like, remember, so alpha and beta have an inverse relationship. So this is sort of like the transformation from tau goes to minus 1 over tau. So this looks like when I take tau goes to minus 1 over tau, that from F we get omega. And if I stopped here, then that would be great. We could sort of collect these functions together and create like a vector valued modular form, or we could reduce to a subgroup. I think gamma 0, 2 is good enough. And we could actually show that f of q is a modular form for gamma 0, 2 with some multiplier system. But the problem is I'm not allowed to stop here because there's extra stuff that comes with this formula. It's 4 square root of 3 alpha over 2 pi integral from 0 to infinity of sinh of alpha t over sinh of 3 alpha t over 2 e to the minus 3 alpha t squared over 2 et. So some kind of mysterious looking integral, and this is the obstruction to modularity. If that wasn't there, we would have an honest modular form. However, even with this, you can get some information about the transformation law for f of q, at least enough to be able to prove this formula using the circle method. And that was done by Dragonet. So maybe what I'll say here is that f, in quotes, wants to be a modular form on gamma 0, 2 with some multiplier system, and I'll just call it new f, whatever multiplier system f has. And people have written this down, but that leads me to my next question, which I'll put over here. Question 2, can we remove this obstruction to modularity? And of course, this is related to question 1. If we're trying to find some structure in the Mach theta functions, well, it would be really nice if we had some kind of modular transformation laws. And that sort of leads to the question of, can we get rid of this somehow? And can we come up with some kind of transformation formula and some structure? What does the order mean? I don't know. Yeah, I don't know. I think that depending on who you ask, you might get some answers to that question. I think George Andrews probably has an answer, and Bruce Barrett probably has an answer, and maybe those answers are the same answer. Probably Atul. Is Atul here? Not here today. If you ask Atul, he probably has an answer. I don't think there's a really good answer to that question. I think for me, the order is a convenient labeling system. Yeah. Okay. So let's talk about this Dragonet thing that I said. So Dragonette. So this would have been in the mid-50s, I think. And then Andrews later in the 60s. George Andrews. This was Dragonette's PhD thesis, followed by George Andrews' PhD thesis. They were students of Rademacher, so maybe what I'm about to write down is not too surprising. But they conjectured, so Dragonette sort of wrote down an asymptotic formula for alpha F. Andrews sort of beefed it up and came up with what he thought was an exact formula for alpha F. And this is going to look very familiar because it looks a lot like the exact formula for P of n. So here we have a sum over C is bigger than 0. Here we need C to be even. And then there will be this thing called AC, and I'll call it AC star of n because it's not the same thing as AC of n. And here we have I 1/2 pi root 24n minus 1 over 6c. Okay, so all of the ingredients are there from before, right? But I think there's a lot to say here. So I'm going to try to say a little bit at a time. The first thing is this fact that C is divisible by 2. C here is coming from the lower left entry of matrices in SL2Z. The fact that C is divisible by 2 is really a mirror of what it says over there, that F wants to be a modular form for gamma 0, 2. Well, that's exactly what this says, okay? So that's cool. So what is AC star? So I'll give you the definition. Depends on if C is even or, if C over 2 is even or odd. Oh, so maybe I'll write this like A2C. So this is minus 1 to the C plus 1 over 2, A2C of n, if C is odd. And it's minus 1 to the C over 2, A2C of n. That can't be right. I think it was wrong. C is even. I think there's something in here that I didn't put. So I will fix this tomorrow. I have this wrong. I think these are correct, but I think there's something in here that's not right. Anyway, the point is that this sum is very close to the same Kloosterman sum as before. It's just this sort of it splits on the evens and the odds. Now, I've never seen this written down anywhere, but I'm gonna put it here because I think it's kind of cute. Maybe nobody knows this but me. I don't know. But this will appear. This will be a line of a paper that I'm writing that will come out very soon. So if I let's instead define some other sums that look very similar to this Whiteman formula. Maybe I should have left it up so that you could still see it, or maybe it's in your notes. Okay, what did I do to Whiteman's formula? Well, I changed 12 to minus 12, and I changed cosine to sine. Well, and there's also a minus sign here, which isn't doing much. But okay, so I really just changed this character from 12 to minus 12. And it turns out that ACNF is equal to, well, it's 0 if C is odd. And it's AC star of n if C is even. And I like this version a little bit better than the other one, simply because it shows off how close we are to the partition function. We really just changed this character from 12 to minus 12. And the sine to a cosine isn't too bad either. So really what I can do here is actually just write this like this, and actually then just remove this condition. And now this really resembles Rademacher's formula in kind of a spectacular way, I think. It's not hard to prove this, by the way. This isn't like some deep thing. I just don't think anybody's ever written it down like this before. Or at least I've never seen it. Now, there's another thing happening here, which is that instead of I 3/2, we I 1/2. And this is related to this graph that I drew yesterday. Do you remember this from yesterday? I said everything in these weights, negative weights and weights that are bigger than 2, everything's good there. Convergence is no problem. But my favorite weights are weight 1/2 and weight 3/2. And these are the ones for which convergence is really hard. So where does the Dedekind-Eta function live? Well, it's a modular form of weight 1/2, but really we want the Dedekind-Eta function inverse for partitions. So it really lives like right here. This is where eta inverse lives. So no issues with convergence whatsoever. But this is where the Mach theta functions live. And so we should expect some convergence issues here. And so I 1/2 is approximately like c to the -1/2 as c goes to infinity. Well, remember the best thing we could do here was c to the 1/2 plus epsilon. And you cancel with that. Well, that's not enough to get convergence. It's just not good enough. And this is why this is a conjecture of Dragonet and Andrews, because it's not even clear that this sum even converges. And that's really the hard thing. If you can prove that the sum converges, there's a good chance you could just prove this. Now we're going to talk about the proof of this tomorrow. So this is a theorem, but just like I said, I'm going pre-2000. So this is a theorem today, but as of this talk, it's not. So right now it's a conjecture. Okay, I think that was all I wanted to say about that. Oh, and maybe this is question 3 that we'll talk about tomorrow. So question 3. Is this conjecture true? Spoiler alert, it is, but we'll get to that tomorrow. Okay. By the way, as I'm erasing, I'll just mention, today I just designed this talk based on how I think about the Mach theta functions. This is not a comprehensive survey on Mach theta functions. It's not everything you might want to ever know. But these are some things that I think about that I think are interesting. And so it's what I happen to pick out. But if you talk to somebody else, like Professor Murty or Atul, you might get some other things. So it's just what I decided to do today. Are there any questions at this point? Okay. What do I have? About 15 minutes? Okay. All right, so let's talk about the order 5. The order 5 Mach theta functions. So these came in the lost notebook. These came with 10 identities. I'm going to write down one of the identities for you in a minute. But remember, there are 10 order 5 Mach theta functions. They came with these 10 identities in the lost notebook. And these, of course, didn't have proofs in the lost notebook. And so for a long time, these were called the Mach theta conjectures. Okay. Let me write down one of them for you. So I already told you what F0 of Q was. That's one of the 5th order Mach theta functions. And the identity goes like this. It looks like -2Q squared M1/5 Q to the 10th plus theta 4, 0. I'm gonna tell you what all of these things are in a second. G of Q. Where MRQ is the following series. So it's a sum from 1 to infinity of Q to the N times N minus 1 over Q to the R Q sub N, Q to the 1 minus R Q sub N. And the reason I wrote it like this instead of just plugging in 1/5 is that all 10 of the identities involve this M function at various inputs. So this is the sort of thing that appears on the right-hand side of all of them. This M is sort of another Mach theta type function. It's not a modular form. Theta 4, 0, Q, this is a theta function. A fairly simple one. So this is a modular form of weight 1/2. So nothing too crazy there. And G of Q is this infinite product, 1 over Q, Q to the 5th, sub infinity, and then Q to the 4th, Q to the 5th, sub infinity. This is the thing, one of the things that shows up in the Rogers-Ramanujan identities. And it's also a modular form. It's a modular form. Each of these is basically a Dedekind eta function. So this is a modular form of weight -1. Well, that's weird. Hold on, is that right? Oh, maybe this is a theta function of weight 3/2. Rogers-Ramanujan is weight 0. Oh, because this isn't exactly, these aren't exactly etas. You have to sort of, yeah, okay, yeah, so that's a weight 0 thing. Yeah, just confusing myself there for a minute. So this is a theta function, a weight 1/2 modular form. This is a weight 0 thing. So this piece here, not mysterious, totally well understood, but these two are essentially Mach theta functions, and so there's this just mysterious identity, and what are we supposed to make of this? So in the 80s, Andrews and Garvin wrote a paper on these Mach theta conjectures, and they proved that there are two families of proved there are two families of 5 identities each. And the truth of any one in a family follows from the others. At least follows from the others in a straightforward way. So in other words, these 10 identities, they said, okay, really there are 5 and 5. And if you prove any one in this family, then you get all 5. And if you prove any one in this family, then you get all 5. Okay, so then they reduced the proof to proving 2 identities. And shortly thereafter, so also in the 80s, maybe both of these papers appeared in the same year, actually. Hickerson proved the identities for F0 of Q and also F1 of Q, which I didn't define for you, but it's one of the other 5th order functions. And those appear in 2 different families, the 0 family and the 1 family. And so the Mach theta conjectures are true from Hickerson's proof. But this proof used, so using Q-series methods. So complicated transformations of Q-series that prove these identities. But if the Mach theta functions really live in some structural modular world, then really there should be a conceptual proof of these identities that really is a modular forms proof. So there's question 4. Is there a modular explanation for these? So is there a proof of the Mach theta conjectures that really uses the structure? Well, if there is some structure, like I said in question 1, if that structure exists, then can we use that structure to actually prove these Mach theta conjectures, and what does that look like? Okay, I have just one more thing to talk about, and that'll be my 5th question, and then I'll be done. So let's talk about order 7, since we've talked about order 3 and order 5. Sorry, I just wrote 3, 7, order 7. So let me tell you what one of the order 7 Mach theta functions looks like. These are usually written with like a script F, again, because Ramanujan's naming conventions left something to be desired. So why did I put that down? I need it. It's q to the n squared over q to the n plus 1 sub n. Okay, so that's one of the 7th order. Remember, there are 3 7th order functions, and this is one of them. They're called F0, F1, and F2. So Hickerson proved the following formula. Q sub infinity F0 of Q. So Q sub infinity, that's basically the eta function. So this thing should be some kind of like weight 1. Well, if F0 is kind of a modular form, then this should be some kind of weight 1 thing. But here's the formula. It's kind of mysterious. So it's a sum over all R and S greater than or equal to 0 minus a sum over all R and S less than 0 of the following thing, minus 1 to the R plus S, Q to the 3R squared over 2 plus 4RS plus 3S squared over 2 plus R over 2 plus S over 2. Now, the exact shape of this thing doesn't matter, like the exact coefficients of this I don't think matter so much right now, but what I want to point out is that this is an indefinite quadratic form. Meaning that as you plug in R and S in the integers, sometimes this spits out positive numbers and sometimes it spits out negative numbers. It's not definite. And there's a well-established theory of sums that look like this when you raise Q to a power that is a positive definite quadratic form. There's a well-established theory. So fact, if Q is a positive definite binary quadratic form, then the sum overall, let's say x in Z2 of Q to the big Q of x, this function is a modular form. Is a modular form of weight 1. For some congruent subgroup with some multiplier system, and there are formulas for computing what the congruent subgroup is and what the multiplier system is based on various invariants of the quadratic form. But the point is that if this is a positive definite binary quadratic form, we know everything about this thing. But what happens when you plug in an indefinite quadratic form up here? I don't know. So question 5, maybe I'll put it right at the bottom here. Question 5 is, what did I write here? Yeah, how does the theory of theta functions, of which this is an example, a theta function associated to a quadratic form, how does the theory of theta functions extend to indefinite quadratic forms? And if we could answer that question, then, well, because of this formula, maybe that can give us some information about at least this 7th order Mach theta function and others. So these 5 questions, I'm leaving them open at the end of today, but hopefully in my talk tomorrow and in Michael's talk tomorrow, we can try to answer all 5 of these questions using the theory of harmonic Maass forms. So that's where I'm going to stop. Thank you.
Thank you so much, Nick. Are there any questions since we have some time? all the identities, they have the same kind of structure where one part you understand as modular and the other part are like Mach theta.
Yeah. Yeah, you mean talking about these identities? Yeah, all of them look like, on the left-hand side, they look like one of the 10 Mach theta functions, fifth order Mach theta functions in Ramanujan's letter. Then there's a piece that is some specialization of this M function. And then there's a piece that's some well-understood weight 1/2 modular form. And I think I think they all involve one of the Rogers-Ramanujan functions, either G or the other one, which I would call H. But yeah, they all have that shape. Different families, yeah. So the families are indexed with all zeros and all ones. And if you prove any one of the identities in either of those families, you get everything. So that's what he did.
Okay, any other questions? If not, so thank Nick again, and we'll break for lunch, and we'll resume at 2:30.